Here we're going to talk about what are called geometric sequences. So for example, consider the sequence 2, 6, 18, 54, and so on. So do you see how I'm getting from one term to one term from another? So I'm taking 2 and I'm multiplying it by 3 to get 6. I multiply that by 3 to get 18, multiply that by 3 to get 54, and so on. So this is an example of a geometric sequence. So specifically, we say a sequence of the form AR squared, AR cubed, and so on is a geometric sequence. So here the A is called the first term. So the first term of the sequence we refer to as, or A is referred to obviously as the first term of the sequence. Now the number that you're multiplying by to get the next term of the sequence, that's called the common ratio. So the common ratio is the number R. So in this first example up here, A is 2, the first term, and then what's the common ratio? Well, that would be 3 because I'm constantly multiplying by 3 to get the next term. So it turns out you can also express the nth term of the sequence making use of A and R. So the nth term, so what term are you looking for? The 100th, 200th, 500th? So whatever term you're looking for, the nth term can be given by the following formula. The nth term is equal to the first term, A, multiplied by the common ratio, R, raised to the n take away 1. So this is our formula. So what you do is you plug in R, your common ratio, you plug in A, and well, you raise R to the n take away 1, and then you multiply that result by A from the order of operations. And that'll give you whatever term you're looking for. It should be noted that the common ratio can be found by taking a term of the sequence and dividing it by the preceding term. So notice if I take AR and I divide it by A, I get R. And same thing with, for example, AR cubed. If I take that and divide it by AR squared, I get R, the common ratio. All right, let's see an example of working with geometric sequences. So let's determine if the sequence 2, -6/5, 18 25ths, -54 over 125. Let's determine if that's geometric, and if so, let's find A and R and the formula for the nth term of the sequence. So this looks like it might be a geometric sequence. The first thing I notice is that it's alternating, right? Positive, negative, positive, negative. So we know that we can go from positive to negative by multiplying by a negative, and then from negative to positive by multiplying by a negative again. Now, if you're going down the road of thinking it might be a geometric sequence, notice that the denominator, 5, 25, 125, those can all be found by multiplying the denominators by 5, so that's a good sign as well. Now to look at what might be the common ratio, like I mentioned, we take a term and we divide it by the preceding term. So I'm going to take -6 fifths, and I'm going to divide it by +2. And so what do I get when I do that? I get -6 fifths times 1/2, and that's going to be negative. Canceling, I get -3 fifths. So if I can get from one term to the other by multiplying by -3 fifths each time in the sequence, that'll mean that this is a geometric sequence. So first of all, 2 times -3 fifths gives this, as is true because this was division. So 2 times -3 fifths gives that. Now the question is, if you keep multiplying by -3 fifths, do you keep getting the next term, the subsequent terms of the sequence? And you do, right? Because -3 fifths times this gives 18 over 25. Multiply that by -3 fifths, you get that, and so on. So this indeed is a geometric sequence. So the first term A is equal to 2. The common ratio R is -3 fifths. Yes, the common ratio can be a negative number. And now the nth term of the sequence, A sub n, is A multiplied by R raised to the n take away 1. So plugging in, A is 2, and then R is -3 fifths. So I'm going to take -3 fifths, and I'm going to raise it to the n take away 1. So that's my formula for the nth term. So if somebody wanted to know what's the 100th term of the sequence, I'd plug 100 in here for n and 100 in there, and I'd evaluate that right-hand side to find the nth term of this, the 100th term of this geometric sequence. Okay, now we know what a geometric sequence is. We can say a few things about what we remember from previous videos, partial sums. So given any sequence A1, and this is any sequence, not just a geometric sequence, A1, A2, A3, dot, 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 AN, dot, 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 recall that the nth partial sum, so nth partial sum, which we denote as S sub n, recall that S sub n is the sum of the first n terms. So it's A1 plus A2 plus A3 plus dot, 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 and it ends at A sub n. That's the nth partial sum of the given sequence. Now, specifically for a geometric sequence, right, the type of sequence we're discussing in this video, we can derive a formula for the nth partial sum. So here's what we're going to do. We're first going to write down what the nth partial sum would be. So S sub n for a geometric sequence is going to be, well, A plus AR, because that's the second term of the geometric sequence, plus AR squared plus AR cubed plus dot, dot, dot. Now let's write it like this. AR to the n take away 2 plus AR to the n take away 1. Now remember, this would be the nth term of the geometric sequence, and the reason is because you're constantly multiplying by r. Now the first term doesn't have an r, right? It's the next term that has that first factor of r. And so how many factors of r do you see? Well, the nth term right here is going to have n minus 1 factors of r, right? Because we started, the first term did not have a factor of r. It was the second term, right? So when you get down here, you don't have n factors of r, you just have n take away 1, because we started one later. We started the second term. Okay, so that would be the nth, that would be an expression for the partial sum of a geometric sequence. Now notice that you can take this partial sum, right? This is just a sum on the right-hand side, and you can multiply it by r. So if I take S sub n and I multiply it by the common ratio r, I simply take that, multiplying the left by r, and I'm going to multiply the right by r as well, and I'm going to distribute the r. So I'm going to get AR, right? This times r is AR. Multiply this by r, AR squared plus AR cubed plus AR to the fourth, right? Down the line, this would become AR to the n take away 1, and then plus AR, and when you multiply this last term by r, you get AR to the n, because n take away 1. R to the n minus 1 times r gives you just r to the n. Okay, so what we can now do is we can take the top, the left-hand side here, and subtract off the left-hand side there. So S sub n, this S sub n, take away R sub n. I'm subtracting left-hand side, take away left-hand side. That's equal to right-hand side, take away right-hand side. Now watch what happens. When you take this top sum and you subtract off this bottom sum, what happens is some terms cancel, right? The AR is going to subtract off with the AR. AR squared, take away AR squared. AR cubed is going to subtract off with AR cubed. Now notice that that A is not going anywhere because there's no A to subtract off here. So this A is going to remain. And after doing all the subtraction, what remains? Well, cancel, 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 cancel. All the way down the line, Rn minus 2 is going to cancel with an Rn minus 2, Arn minus 2 right here. Arn minus 1 cancels with Arn minus 1. And then what you're left with is minus, right? Because you're subtracting off this bottom sum, minus Arn. So it's take away A to the A multiplied by R to the N. So what happened was this term did not cancel from the S sub n, and then subtract off everything except this in the bottom one. And that's why it's a negative right there, right? Because we're subtracting off this whole sum there. So those did not cancel when we subtracted, when we took S sub n and we subtracted off R times S sub n. And so what we can do is we can factor out S sub n here. So the S sub n times 1 minus R is equal to, and factor out an A there, A times 1 minus R to the n. And so we get our formula for the nth partial sum of a geometric sequence. The nth partial sum is equal to A multiplied by 1 minus R raised to the n divided by 1 take away R, right? I subtracted off, or I divided by this 1 minus R there, okay? Let's write it without the parentheses. Let's write it as A times, or rather, let's leave it the way it was, but we'll go ahead and put parentheses around that denominator as well for clarity. parentheses like that. Okay, so this is our formula for the nth partial sum of a geometric sequence. Let's write that down. The nth partial sum of a geometric sequence. Now, of course, you might notice this, that we have one condition, right? That r cannot be equal to 1. If r is equal to 1, this formula does not hold. Okay, so let's go ahead and see an example of making use of this. Find the partial sum, S sub n, of the geometric sequence with a is equal to 2, r is equal to 3, and n is equal to 5. Okay, so we're asked to find the nth partial sum. So from the previous formula, S sub n is equal to a, multiplied by 1 take away r raised to the n, that's in the numerator, and then divided by 1 minus r. Okay, and we're given all these things on the right-hand side. So the nth partial sum is going to be a, which is 2, and then the numerator is going to be 1 take away r, so 3 raised to the nth, and then divided by 1 take away r, so 1 take away 3. So we're looking at the nth partial sum is 2 times 1 minus 3 to the n, and then divided by negative 2. Now notice that we're asked to find the nth partial sum when n is 5, right? So I can simplify here, and I can also plug in 5 for n. So let me first simplify. So S sub n is equal to, canceling here, it's going to be negative 1 multiplied by 1 minus 3 to the n. Okay, so that's for the nth partial sum. And then if I plug in 5, I get specifically the fifth partial sum is equal to negative 1 multiplied by 1 minus 3 to the fifth. So I'm looking at S sub 5 is negative 1 multiplied by 1 take away 243. So S sub 5 is equal to negative 1 times negative 242. So the fifth partial sum is 242. Okay, what's the meaning of that? Well, the meaning is that if you add up the first 5 terms of the sequence, we're multiplying by 3, right? So it's going to be 6, 18, 54, and then what's the next one going to be? Times 3 is 162, right? If you add up, double check that, 3, 12, yeah. So if you add up those terms, if you add those together, you're going to get 242. That's the meaning of the fifth partial sum, in this case of this geometric sequence. Okay, so now it turns out that we're not always interested in finite sequences. It turns out sometimes we're interested, or sorry, I should take that back. Sometimes we want to ask ourselves what happens as you let n get larger and larger. What happens to the partial sums as n increases? And we'll see some situations where, kind of counterintuitively, that value does not necessarily go to infinity. Okay, and so now we're starting to kind of bridge the gap to calculus, and we'll talk about that, something like that in the next video. Until next time.